Fourth one, differential equations. First one, RL series circuit. RL series circuit. Now consider a circuit containing resistance R and inductance L and the battery E Consider a circuit containing resistance R capital R and inductance capital L in series with a voltage source E battery with a voltage source E, that is a battery as shown in the figure. Adjacent figure. Now, if I be a current at any time in the circuit, so we considered the circuit containing the resistance R, inductance L and the voltage source battery. This is the circuit we considered here. Now we have to model this circuit now by applying the Kirchhoff's voltage law. As we explained earlier, Kirchhoff's first law is the voltage law. Now, by applying the Kirchhoff's voltage law, so we have to write if I be the current in the circuit, at any time t, then the charge q on the condenser is equal to integral I dt. That implies q is equal to integral I dt. Therefore, I equal to dq by dt. Since differentiation and integration are the reverse process of each other, inverse of each other, we are writing I is equal to dq by dt. Now, applying Kirchhoff's law. Now, applying Kirchhoff's law, we have sum of the voltage drop across R, L and R and L equal to E, as explained in the symbols, quantity and unit of measurement. There I explained. So q is equal to integral I dt, or I is equal to dq by dt. In the relations I explained, I is equal to dq by dt, or q is equal to integral I dt. Now applying the Kirchhoff's law, so sum of voltage drops across R, that is by Ohm's law, that is equal to Ri, across L, that is equal to L into di by dt, is equal to electromotive force E, is equal to electromotive force E. That is voltage drop across the resistance plus across the inductance is equal to electromotive force, EMF, electromotive force, EMF. Therefore, voltage drop across R is R into I by Ohm's law, plus voltage drop across inductance is L into di by dt is equal to electromotive force. Here is battery, constant power E. Therefore, this can be written as L into di by dt plus R into I equal to E. This is a linear differential equation of first order, and this can also be written as since we know that I is equal to di by dt, I is equal to dq by dt, not di by dt, I is equal to dq by dt. Therefore, substituting I value, this can also be written as L into d by dt of dq by dt plus R into dq by dt equal to E. Therefore, this can be written as L into d by dt of dq by dt, that is d square q by dt square plus R into dq by dt is equal to E. Since here I is equal to dq by dt, we are substituting I value, that is from basic relations, I is equal to dq by dt. Therefore, we got L into d square q by dt square plus R into dq by dt is equal to E. This is the desired differential equation of the circuit. Equation of the circuit, given circuit. This is the differential, desired differential equation, required differential equation of the circuit. So after modeling the given electrical circuit by using the Kirchhoff's first law, we got this linear differential equation of second order in terms of charge q. We got linear differential equation of first order in terms of I, in terms of I, L into di by dt plus Ri is equal to Q. First order in terms of I, second order in terms of Q. This is the desired differential equation of the circuit. Next, LC circuit. Consider an electric circuit containing capacitance and inductance, capacitance C, inductance L, current I. Here we considered this electric circuit containing inductance L and capacitance C. Consider an electric circuit containing an inductance capital L and capacitance C. So this is the electrical circuit having capacitance C, inductance L. Now we have to form the differential equation for this electrical circuit by applying Kirchhoff's voltage law. First law, let I be the current and Q be the charge in the condenser plate at any time t. At any time t, so that the voltage drop across inductance L is equal to L into di by dt Q, or this is equal to L into d by dt of dq by dt, since I is equal to dq by dt. Therefore, this is equal to L into d square q by dt square. So L into d square q by dt square, since I is equal to dq by dt, and the voltage drop across C, and the voltage drop across C is equal to q by C is equal to q by C, as there is no applied EMF, electromotive force, in the circuit. By Kirchhoff's first law. Therefore, by Kirchhoff's first law, that is voltage law, Kirchhoff's first law, we have there is no EMF, applied EMF, in the given LC circuit. Therefore, right hand side is equal to voltage drop across the circuit is V suffix C, V suffix L is equal to 0 by applying the Kirchhoff's voltage law, that is first law, as explained in the Kirchhoff's first and second law. That is V suffix L plus V suffix C equal to, here there is no applied electromotive force, therefore this is equal to EMF. Therefore, there is no applied electromotive force. This is V suffix L is L into di by dt plus Q by C is equal to no electromotive force here, that is equal to 0. So electromotive resultant electromotive force is a 0 here, as there is no applied electromotive force in the given circuit. Therefore L into di by dt, this can also be written as we have written in the above, L into d square q by dt square. Therefore L into d square q by dt square plus q by c equal to 0. So this is in terms of q, or this can also be written as L into di by dt plus 1 by c into integral I dt, since q is equal to integral I dt, since q is equal to integral I dt, by the basic relations we have to write in terms of I, this is in terms of q. In terms of q, this is a second order differential equation. In terms of q, it is a first order differential equation. This can also be written as integral differential equation, as it is having both derivative and integration. So it is called integral differential equation. This is the desired differential equation of the given LC circuit. This is 2. Third one, or LC series circuit. Now consider a circuit containing resistance or inductance L and capacitance C, as shown in the diagram. This is R, resistance. This is L, inductance. This is C, capacitance. E, battery, constant power. I, therefore now consider a circuit containing resistance or inductance L, resistance or inductance L, and capacitance C, as explained earlier. These are all passive elements, all in series with a constant electromotive force. Constant EMF, electromotive force, capital E. It is an active element as explained earlier in the beginning of the topic, applications of differential equations to electrical circuit. Now, if I be the current in this circuit at any time t, if I be the current, rate of change of flow of current with the current in the circuit at a time t, then the charge q on the condenser I be the current in the circuit at any time t, and the charge q on the condenser equal to integral I into dt. That is I equal to dq by dt. Since the differentiation and integration are the inverse of each other, so therefore I is equal to dq by dt. Now applying Kirchhoff's law, we have sum of the voltage drops across R, L and C is equal to resultant electromotive force E. That is voltage drop across resistance, voltage drop across inductance, voltage drop across capacitance is equal to resultant electromotive force. So that is here EMF. Therefore, this can be written as by Ohm's law. This is equal to R into I plus voltage drop across inductance L into di by dt, voltage drop across capacitance Q by C is equal to EMF is here battery E. Therefore, this can be written as L into di by dt plus R into I plus 1 by C into Q. This can be written as integral I into dt is equal to E. This is our linear integral differential equation. This is a linear differential equation in terms of I. So if you can write Q is equal to integral I dt, this is becomes a integral differential equation, or this can also be written as R into I, that is dq by dt plus L into d by dt of I is equal to dq by dt plus q by c is equal to E. Since I is equal to dq by dt. Therefore, first we are writing L into d square q by dt square plus R into dq by dt plus Q by C is equal to E. This is our desired differential equation in terms of Q for the given LCR circuit. For the given LCR circuit, after applying the Kirchhoff's first law, that is voltage law for the given circuit, this is the modeling of the electrical circuit by applying Kirchhoff's voltage law. This is our desired differential equation for the given electrical circuit. These are the three cases we discussed here to solve the problems regarding electrical circuits.